It all began with an apple. At least that's the story they tell. A young man sits under a tree. An apple falls. And in that moment, he conceives a theory that will change our understanding of the universe forever. But the truth is far more complex and far more profound. The man was Isaac Newton, and what he uncovered wasn't just a law of motion or a clever insight into falling fruit. It was a unifying principle that connected the heavens and the earth, the planets and the tides, the ordinary and the infinite. It was a discovery so powerful it redefined science itself. Before Newton, the world was fragmented. The physics of Earth and the motions of the stars were seen as separate realms. Aristotle taught that objects in the heavens obeyed different rules than those on Earth. The planets moved in perfect circles, guided by divine forces. Objects on Earth, meanwhile, fell because they were seeking their natural place. Science had explanations, but not coherence. Then came Newton. Born prematurely on Christmas Day in 1642, the same year Galileo died, Newton would grow up to become one of the most brilliant and enigmatic figures in human history. In 1665, when the plague closed Cambridge University, he returned home and entered what he would later call his annus mirabilis, his year of miracles. He was just 23 years old. In that single year, he developed the foundations of calculus, formulated the laws of motion, and conceived the theory of universal gravitation. 3 breakthroughs that would each, on their own, define a genius. But Newton did all of them simultaneously. What made his gravitation theory revolutionary was not simply that it explained why things fall. It was that it offered a single, elegant formula that described everything, from an apple dropping from a branch, to the moon orbiting the Earth, to the planets circling the sun. His insight was radical. The same force that pulls an object toward the ground also keeps the moon in its path. Gravity is not confined to Earth. It acts everywhere, always with predictable precision. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Simple, elegant, terrifyingly powerful. With one equation, Newton unified the heavens and the earth. He replaced mysticism with mathematics. Suddenly, the cosmos wasn't unknowable, it was understandable. The universe was a machine, and Newton had found its blueprint. But Newton didn't stop there. In 1687, after years of silence and perfectionism, he published the Philosophia Naturalis Principia Mathematica, known simply as the Principia. It was written in Latin, dense and uncompromising, but within its pages lay the foundation of modern physics. The Principia didn't just lay out the law of gravitation. It introduced Newton's 3 laws of motion, principles that still govern how we understand force, inertia, and acceleration. First, an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. Second, the acceleration of an object depends on the mass of the object and the force applied. Third, for every action, there is an equal and opposite reaction. These weren't just abstract rules. They were tools to predict the future. Given enough information, Newtonian mechanics could tell you where a planet would be 100 years from now, or where a cannonball would land in 5 seconds. Determinism, precision, control. For the first time in human history, the universe seemed comprehensible, even predictable, and the scientific world was stunned. Newton's theory of gravitation allowed astronomers to explain planetary orbits with unprecedented accuracy. It confirmed Kepler's laws of planetary motion. It explained the tides. It predicted the shape of the Earth. It even allowed scientists to detect unseen planets, like Neptune, based on gravitational irregularities in nearby orbits. Suddenly, everything made sense. This was more than science. This was a new worldview. Newton's universe was clockwork, precise, elegant, and governed by immutable laws. There was no need for divine intervention in the daily running of the cosmos. Everything, from the falling of a leaf to the movement of galaxies followed the same set of rules. But Newton himself was not as mechanical as the universe he described. He was secretive, obsessed with alchemy, consumed by biblical prophecy. He studied ancient texts, searched for hidden codes in scripture, and believed he was chosen by God to decode the universe. He never married. He had few close friends. And yet, from this solitary, mystical mind emerged the most rational framework science had ever known. Perhaps that's what makes Newton's genius so fascinating. He was not just a scientist. He was a philosopher, a mathematician, an alchemist, a mystic. He lived in the age of reason, but kept one foot in the world of magic. And somehow from that contradiction emerged the foundation of modern science. Today we live in a world built on Newton's discoveries. Every rocket launch, every GPS satellite, every physics classroom. They all trace back to that falling apple, to that 23-year-old in rural England, to that mind that dared to ask not just why, but how. Isaac Newton didn't just discover gravity. He discovered order, predictability, the idea that the universe could be explained, not merely worshipped or feared. And in doing so, he gave us the most powerful tool humanity has ever known, the ability to understand the universe itself. But this is only the beginning of Newton's story. Because with great understanding comes a new kind of question. If the universe runs like a machine, where does that leave us? Are we just gears in a cosmic clock, or something more? And how far can Newton's laws truly take us before they break? For decades, Newton's laws stood unchallenged, so powerful, so accurate, that they seemed untouchable. They explained the orbits of planets, the motion of comets, the trajectory of projectiles. Engineers built machines based on them. Astronomers predicted eclipses to the minute. Newtonian physics became the foundation upon which the modern world was constructed. It wasn't just that his laws worked. It was that they gave people a sense of certainty. The universe, once chaotic and mysterious, was now a giant machine, predictable, understandable, controllable. The age of superstition was ending. The age of reason had begun. But Newton's success came with a hidden cost. His equations worked so well that they became unquestioned. For 2 centuries, scientists assumed that everything could be explained through his framework, given enough time, enough data, enough precision. This view of the universe as a deterministic machine influenced not just science, but philosophy, politics, and even human identity. If everything follows fixed laws, then what is free will? If all motion is predictable, then are our thoughts and actions just the output of complex chemistry and physics? Newton's mechanics didn't just describe the physical world, they shaped how we saw ourselves within it. Still, for all its triumphs, Newtonian physics had cracks. Small ones, subtle inconsistencies, anomalies that didn't fit the model. One of those cracks came in the form of light. Newton believed light was made of particles. He even performed experiments with prisms to show how white light splits into a spectrum of colors. But others, like Christian Huygens, argued that light behaved like a wave. For centuries, the debate continued. Was light a particle or a wave? Newton's authority kept his view dominant, but the evidence was never conclusive. Then came electromagnetism. In the 19th century, James Clerk Maxwell formulated a set of equations that unified electricity and magnetism. His theory predicted that light was an electromagnetic wave traveling at a constant speed. That speed, approximately 300,000 kilometers per second, would become one of the most important constants in science. But here's where the real trouble began. According to Newton's laws, motion is relative. If you throw a ball from a moving train, the speed of the ball depends on both your throw and the train's speed. So logically, if light moves at 300,000 km/s, it should appear slower or faster, depending on whether you're moving toward it or away from it. But that's not what experiments showed. No matter how fast you moved, light always traveled at the same speed. Always. It didn't matter if you were moving toward the source or away from it. Light behaved the same. This defied everything Newtonian physics stood for. And it suggested something deeper, that time and space themselves might not be as rigid as Newton believed. This mystery would haunt physicists into the early 20th century. Meanwhile, another anomaly appeared: Mercury's orbit. All planets follow elliptical orbits as predicted by Newton's laws. But Mercury's orbit precessed, shifted slightly, in a way Newtonian physics couldn't fully explain. The deviation was tiny but persistent. Astronomers looked for hidden planets, unseen forces, errors in measurement. Nothing worked. The math was too precise for Newtonian gravity to be wrong, yet the evidence was clear. Something wasn't adding up, and that's where Einstein enters the story. In 1905, Albert Einstein published a series of papers that would reshape physics. One of them introduced the theory of special relativity. It proposed that the speed of light is a constant, not because light is strange, but because time and space adjust to keep it constant. Time slows down, length contracts, reality bends to preserve the speed of light. This wasn't just a correction to Newton, it was a revolution. Special relativity replaced Newton's absolutes with Einstein's relatives. There is no universal clock, no single measure of space. Everything depends on your frame of reference. Newton's laws still worked, but only as approximations, useful but not fundamental. 10 years later, Einstein took it further. In 1915, he presented the general theory of relativity, a new theory of gravity. According to Einstein, gravity isn't a force pulling objects together. It's the curvature of space-time caused by mass and energy. The Earth orbits the Sun not because it's pulled by an invisible force, but because it's moving along the curved geometry of space. And guess what? Einstein's equations perfectly explained Mercury's orbit. For the first time in centuries, Newton was surpassed. But that didn't mean Newton was wrong. In fact, to this day, we still use Newton's laws to launch rockets, build bridges, and simulate motion. His equations are embedded in computer code, engineering software, and the laws of classical mechanics. They're just not the whole picture. Think of Newtonian physics as a map, accurate for short distances, familiar terrain. But if you go far enough, fast enough, close enough to a black hole or to the speed of light, the map begins to distort. That's when you need Einstein's version of the universe. Still, Newton's legacy is secure. He gave us the tools to begin asking deeper questions. He transformed science from speculation into precision. He showed that the universe is governed by laws, and that those laws are discoverable. His gravitation theory was more than a calculation. It was a statement of belief that the cosmos is rational, that order exists behind the chaos, and that the human mind can uncover it. So while relativity and quantum mechanics may have refined the picture, the frame remains Newtonian. He didn't just explain motion, he taught us how to see the universe. And in doing so, he laid the foundation for every scientific revolution that followed, including the ones that proved him incomplete. Newton's influence didn't end with physics. His ideas spilled into every corner of human thought: philosophy, politics, economics, even theology. Because once you prove that the universe follows laws, the natural next question is, what else follows laws? Thinkers in the 18th century, known as the Enlightenment philosophers, took Newton's worldview and ran with it. If motion could be predicted, perhaps so could society. If gravity could be described with mathematics, maybe morality, reason, and progress could be too. The world, it seemed, was not built on chaos, but on logic, on rules, on structure. This ushered in an era of profound optimism, a belief that humanity could shape its destiny through knowledge. Newton became the symbol of what was possible when reason triumphed over ignorance. His name was invoked in debates about government, science, and education. Voltaire called him the greatest man who ever lived. Alexander Pope famously wrote, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." But as Newton's ideas spread, they began to create a paradox. If everything could be explained, where was the space for wonder? For mystery? For free will? The Newtonian worldview was so precise, so mechanical, that some began to fear its implications. Were we just complex machines obeying unseen formulas? Was the soul just an illusion of chemistry? Were love, creativity, and consciousness just side effects of particles and forces? This tension between the beauty of Newton's laws and the existential dread they implied would linger for centuries. And then, in the 20th century, came another rupture. One that would shake the foundations of Newtonian certainty even more than Einstein: quantum mechanics. While Newton had described the world at human scale, planets, projectiles, machines, quantum physics looked inward, into the realm of atoms and subatomic particles. And what scientists found there defied everything Newton had taught. In the quantum world, particles didn't move along predictable paths. They existed in states of probability, only choosing a position when observed. Cause and effect became blurred. Reality itself appeared to depend on measurement. Determinism gave way to uncertainty. The famous Heisenberg uncertainty principle stated that you can't know both the position and velocity of a particle with perfect precision. The more you know one, the less you know the other. This wasn't a limitation of technology, it was a fundamental feature of reality. And then there was Schrödinger's cat, the thought experiment that showed how quantum objects can exist in superpositions, both alive and dead, both here and there, until observed. None of this fit into the neat mechanical framework of Newtonian physics. The clockwork universe was crumbling, and yet Newton's laws still worked. They still described the motion of baseballs, cars, and planets. They still governed the world we interact with every day. This duality of classical predictability and quantum strangeness became the new normal. Newton's world wasn't wrong, it was just incomplete. A special case, a macrocosm that breaks down under extreme conditions. But Newton's legacy persisted. His approach to science, observation, mathematics, prediction, became the standard. Even in the quantum realm, physicists use Newtonian approximations for large systems. And in the cosmic realm, general relativity often reduces to Newtonian equations when dealing with weak gravity and slow speeds. In other words, Newton built the scaffolding. Einstein and the quantum pioneers expanded the building, but the foundation remained his. Even more remarkable is the fact that Newton didn't see himself as just a scientist. He spent more time studying alchemy and biblical prophecy than physics. He wrote hundreds of thousands of words on hidden codes in scripture, on the dimensions of Solomon's temple, on the end of the world. He believed the universe was a divine cipher, and his role was to decode it. This aspect of Newton is often ignored, but it's essential, because it shows us that even the greatest mind in scientific history was still driven by mystery, by faith, by a desire to find purpose beyond equations. Newton's science wasn't cold or detached, it was spiritual. He believed that understanding gravity brought him closer to understanding God. And perhaps that's the most human part of his genius. He didn't divide science and wonder. He unified them. Today we remember Newton for his laws, his math, his logic. But what made him truly revolutionary was his vision that the universe, in all its complexity, was knowable. That the same laws that moved the planets also governed apples, oceans, and time. It's easy now to take that for granted. We live in a world where we expect explanation. We demand it. But that expectation exists because of Newton. He rewired our assumptions. Before him, the world was filled with divine mystery. After him, it was a puzzle we could solve. And we've been solving it ever since. With every telescope that peers deeper into space, with every particle collider that probes the fabric of matter, we are living in Newton's legacy. We are still asking the same question he asked under that mythical apple tree. What holds the universe together? And behind that question, a deeper one still. If we can understand the cosmos, what does that mean for our place within it? Isaac Newton didn't just uncover a force. He revealed a principle, that the universe is governed by order, not chaos. That behind every falling apple, every orbiting moon, every rolling wave, there are patterns, laws, logic. He gave us the language to describe the cosmos. Not with myth or magic, but with mathematics. And in doing so, he changed not just science, but the human story. Because once we knew that nature could be explained, we began to believe that everything could. His legacy is not just gravity. It's the very idea that truth can be discovered, that knowledge can be built, that the universe is within reach. Today we live in a world lit by the sparks of his vision, and every time we launch a satellite, predict an eclipse, or simply drop a pen and watch it fall, we are still, in a way, sitting under that apple tree, not just watching, but understanding.